Hello everyone, welcome to my presentation. My name is Yanpeng Su. I am a student at the University of Erlangen-Nuremberg. My supervisor is Dr. Maximilian Lübke. In this video, I will introduce my project on designing a CO-PMCW-based vehicular ISAC system using Simulink. Vehicular information systems play a critical role in the development of intelligent transportation systems and autonomous driving. It relies on vehicular communications for data exchange and automotive radar sensing for environment perception. The idea of integrated sensing and communication has gained a lot of attention these years, since it allows them to share the same resource and thus avoiding interference, improving efficiency, and reducing costs. This work focuses on the waveform and physical layer design for vehicular ISAC systems. The phase-modulated continuous waveform is used due to its strong radar performance and excellent anti-interference capabilities. However, it faces the challenge of low communication spectrum efficiency due to the radar parameterization. The goal of this work is thus to design a system overcoming these shortcomings on Simulink and test its performance in automotive applications. Our solution is to transmit the pilot and data sequences in a parallel scheme. The radar sensing system only uses the pilot sequence, thus freeing the data sequence from radar parameterization and allowing a higher data rate. Furthermore, the communication receiver can track the channel state information using the continuously transmitted pilot, thereby improving performance in fast-feeding channels. The model system is shown in this diagram. We consider the scenario with two vehicles on the route. One vehicle serves as the transmitter, sharing information with the other vehicle, while simultaneously collecting reflect signals to perceive the surrounding environment. The channel characteristics are extracted from channel simulation in an external channel simulation software, waveform. The transmitter, communication receiver, and radar receiver each consist of an RF converter and a baseband processor. The transmitter generates the parallel transmitted pilot and data sequences. The transmitted signal constellation diagram is shown here, including the data signals in the real part and the pilot signals in the imaginary part. At the communication receiver, we use a RIC receiver combined with maximum ratio combining technology. The channel estimation process involves a correlator for signal detection and then calculates the weight factors for maximum ratio combining. The estimated channel factors can be monitored in a real time using displayers. Based on the result of channel estimation, the multi-path faded signals are separated and processed by the sub-receivers. At last, the output of the sub-receivers is combined for final detection. The architecture of a sub-receiver is given in this diagram. The enabler controls the synchronization of the sub-receivers. The received signal is first multiplied with the weight factors and then dispersed. The resulting signal is subsequently forwarded to the final detector for combination and data detection. We can monitor the beta rate of the receiver on the data displayer and check the transmitted and received data symbols through the scope. The radar receiver architecture is depicted in this diagram. It uses the correlator bank for delay and range estimation, while the Doppler and velocity are determined by FFT. The radar receiver finally produces a range Doppler map as the result. Additionally, I'd like to introduce the RF blocks used in this work. The RF devices are responsible for frequency modulation and analog signal transception. Both the transmitter and receiver side include a mixer for frequency conversion, a bandpass filter, and an amplifier. In the next step, I will show you the performance of our model in realistic use cases. We simulate the channel conditions in Leipzig Plus in Berlin using an external channel simulation software, waveform. In the simulation, this car serves as the transmitter and radar receiver, and this car serves as the communication receiver. The simulated channel parameters are then imported into our model, and we evaluate the beta rate and range Doppler map of our system, analyze how they change as the cars move. We set the relay feeding channel for two systems. For communication, we only extract the dominant paths, since other paths are below noise and cannot be detected. For radar sensing, considering the high processing gain, all the paths are extracted. In this project, we designed an improved CO-PMCW-based ISAC system on Simulink and tested its performance in vehicular systems. In the simulation, a low beta error rate is always guaranteed, and the surrounding objects are always observable on the range Doppler map, reflecting a good applicability of the system in realistic scenarios. In the future, we plan to investigate the impact of the interference produced by the parallel transmission and try to mitigate it. In addition, the problem of Doppler intolerance, which is a common problem for PMCW-based radar systems, should be addressed. Thank you for watching. I wish you have a nice day. Goodbye.